All right. Okay, we might get underway. Thanks. Thanks for coming along. We had. I'm really looking forward to this talk. I'll just start off with that. I got in contact with Mars after I saw a LinkedIn message post about Mars doing a talk with a whole bunch of kids, and I was really inspired by this post, and I thought, I wonder if we can get her along to give us a talk on something. And so I made contact with Mars through LinkedIn, and I just have to say, you were so enthusiastic about it. And I thought, oh, this is absolutely fantastic. So Mars is a PhD candidate with joint candidacy with UTAS and CSIRO. Mars is a computer scientist, and I think you'll see some of the things that you get up to. So without further ado, across to Mars.
Thank you. Thank you so much for having me today. I was really excited to be invited because I've actually been a fan of you all for ages. I was saying that my husband and I don't own a car since we moved to Tasmania. It's just sat in the driveway for ages. Everything's so walkable except for this one clubhouse. So I've just been watching you from afar going, how am I going to figure out how to do a hobby where I'll have to walk home for 2 hours on a Wednesday night? But it looks very, very fun. I follow you all on social media and through newsletters. I had your book sitting on my desk for multiple years, just dying to get a call sign of my own. And I would love to hear all of your stories afterwards about lightning and moon bounce and everything. It's fantastic. I love it. But I will just start off with introing my topic, because then I can also intro kind of where our skills overlap, which I think is important here, because some questions you'll ask and I might have great ideas, and some of them might go straight over my head. But I'm going to talk to you today about space junk and the role amateur radio can play. I would like to begin by acknowledging the traditional owners of the land that we meet on today. It's a beautiful, beautiful area around Hobart that has lots of pristine views. I've never been up here before. It's a fantastic, fantastic spot, not just for these sight lines to maritime radio, but we're here on the lands of the Muwinina and the Palawa people, and we would like to pay respect to them today. I'm Mars, as you've heard, Mars like the planet, and I'm a computer scientist by training. That's what I did at university, and that's what I've gone on to do in industry. I write books, I've worked for companies, I am a freelancer, I do tech stuff, but then as a sucker for punishment, I went back to do a PhD at UTAS and kind of got railroaded into doing something to do with antennas. And so when I initially, in 2020, planned to start a project that was about analysing data that came from radio telescopes that had already been through multiple astronomers who knew all about that front-end stuff, and then got to me to kind of extract wisdom from with the data analytics and machine learning and high-performance computing background I had. Instead, COVID happened, and antennas happened, and as you know, in the real analog world, sometimes things don't go to plan, and I've ended up with a very front-end, very hardware kind of project. So that's my job as a PhD candidate at UTAS and CSIRO, and then on the side, I'm also a software developer for a state government-funded project for UTAS, where I work on UTAS telescopes as well. So I work on CSIRO telescopes, I work on UTAS telescopes, and in my free time, I also contribute to some open source hardware and software and standards for other radio telescopes around the world, and on the side, just for fun, I'm a science communicator, try and stop me. I will tell all of your kids about space. I go to libraries and hobbyist meetups, and I make videos and activities, and I sometimes get paid to make activities which they then use to teach things in classrooms, which is best. So I count this little folded dipole antenna down the bottom, I think it's 64 of them, as very low frequency for radio astronomy. Usually I'm up here, L-band 3 mil. We do get a bit of S-band stuff. That's probably about as low as I go typically when we're talking about satellites. And so when we're talking about high frequency, low frequency, we're definitely going to get a bit of a terminology disconnect. But I'm going to start by saying I'm not an astrophysicist, and I cannot tell you how the wonders of space work. I can tell you some of the systems that we use to examine or interact with space, how those work, and even how a few of the systems that go into space work. And I would also say that anything prior to the digitizer is basically words and magic. By the time I come in, usually somebody has sourced, picked, purchased, sourced all of the hardware, sometimes operated for 50 years before I come into the scene, so that's quite nice. Software and higher level processes are my jam. But today I thought I'd go through a bit of what space junk is and where radio comes into space junk tracking, or just space tracking in general. Some of the stuff we've done in Tasmania, some of the stuff that amateurs have... Is that a word? You all seem to use this word. It seems kind of disparaging. Amateur radio. Every time I hear it. It's lovely that this is a term we've arrived on. That amateurs have contributed to space stuff. And then some ideas for the future, which, as Justin mentioned, I have espoused far and wide about how I think that citizens should be able to contribute to all sorts of things, and are not necessarily included in some of the systems that would allow them to do so. So that's where we'll end up in the pie in the sky ideas. But what is this space junk anyway, and why should it matter to you personally? You're not a satellite, this probably has no bearing on you, right? Well, if we look at Earth as this little circle in the middle there, I updated all my screenshots today so I can say that they're perfectly updated. Orange is the active satellites, and the other colours are everything else. And these are just the things that attract and have numbers that we know about. And so when you put a satellite into space, it has a job to do. They have all different jobs. They end up in all different parts of space. They stay there for different amounts of time, and they have different levels of sophistication in their hardware design. But usually to put it up there, we have a multi-stage rocket, because thrust is hard and getting out of orbit is hard. And so we use multi-stage rockets where each stage is slightly smaller, so it can shed weight. You use the big rocket fuel tank. You don't want to carry around this empty rocket fuel tank. You purge it. Now you've got a smaller one. It's lighter. Now it's still full of fuel. It purges it. And so at a certain point, usually that first stage will drop back down to Earth. Second and third stages, they make it to orbit before they're detached. They're stuck in space. They'll take a while to come down. And when we see things that go shattering across the sky and they show up in the news, space junk falls to Earth. That's usually what they are. They're rocket bodies. They're huge. They're the size of a school bus. We just left them up there empty, sometimes still a little bit full of fuel, just enough that they're an explosion risk. Really deadly fuel and coolant. We also have lots of satellites that were put up there that then ran out of batteries, and they were put in such high orbits that it's going to take hundreds of years for them to come back down, even if they are going to at all. Sometimes they were put in, when we put something up there, we want it to have its great lifespan, and when we didn't know that this was going to be a problem, we wanted to put them in the longest lasting, most stable orbits ever. It turns out that's a terrible idea.
We even have satellites that come back to life.
Yes.
We've got amateur satellites that have come back to life.
Oh, that's incredible.
Because their batteries have shorted out and it's only running on solar cells.
Well, I guess if you could also have something that if you transmitted enough to it, probably have a passive, I don't know, I'm not on radio enough to tell you whether you could have a passive powered satellite that you just transmit out to induct power. But lots and lots of reasons why things end up here. There's not just rocket bodies. Sometimes when astronauts go up to fix things on the International Space Station, then whatever module they've just replaced, it's not feasible to bring it back down, they chuck it out into space. Quite often when we're going to launch something into space, like people or expensive robotics, we first do a couple of test launches where we just make a big solid piece of metal that's about the same weight distribution as the thing we're going to launch, and then we launch that into space to see if it stays up there. Call them boilerplate spacecraft. All of this becomes junk. This and many more times. That time when Elon Musk put a car in space, that's junk. They're all junk. And unfortunately, when you put this much stuff up there, it's not just a big traffic jam. They're collision risks with each other. Because each of these objects, in the outer orbits, they're orbiting at the exact same rate as the Earth is rotating. That's why we call it geostationary orbit. But as you get closer to Earth, the gravity gets stronger, and so the orbits get faster. And so in low Earth orbit, which is that real close, tight shell around Earth, that's where most of our communication satellites are, because we want the travel time to be as low as possible. We want to have good coverage. They're going about 27,000 kilometers an hour. That's about 10 times the speed of a bullet. If you have two of those hit each other from opposite directions, then the relative velocity is twice that. And so you get these incredible impacts. This is the largest satellite debris forming collision that we have on record. This happened in 2009. Two mobile communication satellites hit each other at full speed, going perpendicular to each other, so not as bad as it could have been, but they created 2,000, sometimes 3,000 pieces of debris, depending on who you ask, on who's modelling. As you can see, because of that orbital dynamic that keeps them going around in orbit, that's the same thing that spreads the debris far and wide. Now, if you're looking at this, 15 years later, it's actually created the shell of all these objects that we've seen that have ended up little shards of metal and glass. Terribly deadly. So if each one of these objects at that speed is capable of the force destruction of the original impact, then we have more than 2-3 orders of magnitude of destruction capability from that one destruction, that one collision. And we see this, that on average, every collision creates debris that is capable of at least 10 times the destructive capability of the original. So we have this theoretical model come up with by Kessler, which is why we call this Kessler syndrome. This was a theory come up with by Donald Kessler, who was modelling how asteroid belts form at NASA. That you think you have big rocks and then they would slowly smash and they would slowly become more evenly distributed, more evenly sized little rocks that make a belt. That space debris could work this way with a suitably populated orbit. More and more of them could smash into each other, thus exacerbating the risk of collision to other things and slowly forming a homogeneous swirling field of tiny debris that nothing could get through. Then we would just lose access to orbit. And the worst part is the lowest orbits are the ones that are highest risk of this. So even if the higher orbits are still good, if you can't get anything through it at launch, it doesn't matter. And if we can't have satellites, even though we don't necessarily think of them as a thing we rely on all the time, but we actually do. We use them 1,000 times a day. We use them for maps and navigation. That's why you don't ever have to pull over and flip through your street directory anymore. We don't have remote communications, where Australia is one of the most space-reliant nations in the world, because we have things like 11% of the world's airspace and 0.3% of the world's population, and we have all of these huge distributed systems where we rely on enormous amounts of coordination and automation to even produce food. We need satellites. We need it to model how the climate is changing and to see how cyclones are moving and to be able to use satellite imagery to tell when water sources are polluted with cyanobacteria and algae, to see how land use changes over time, to see whether we're using up too much forest, to see if there's bushfires in the middle of nowhere so that we can tell that they're coming before they hit the edge of suburbia. And we don't get space telescopes, which maybe you don't care about, but I do. Because otherwise we're just looking through the atmosphere, we can see so much less, because you would know about atmospheric capacity, of course. So all of these different services that we don't necessarily think about will just evaporate overnight. And I'm sure also knowing about solar weather, you also know that something like a Carrington event could result in the same thing. It might not necessarily be physical destruction, it could be electromagnetic destruction of these critical infrastructure devices in orbit. And so what do we do about it? Well, we can't necessarily stop them crashing into each other, but what we can do is tell when they're going to crash into each other, just in case one of them can move out of the way. And so we have these networks of sensors all over the world, different networks. This is just one of them, but you can see they're not that great and they're not very well distributed, of sensors that look at the sky all day, every day, and see where things are, and update a model that then feeds in to computers that run simulations based on what we know about how things move in orbit to see if any of them are going to hit each other, and if they look like they're going to, we figure out if either of them have maneuvering capability, we get someone on the phone. And then they play a game of chicken, because if both of them are fueled and have maneuvering capability, everyone wants the other guy to use up their fuel, which is very silly. But we have this constant update, and they use this fun, archaic, slightly older data format until a little bit recently we've slightly evolved past this. But it is still very true that most of our communications are done in this punch card format, where you get this little bit of information about something's orbit, and then you use that to do all these complex simulations. So even though we make these simulations have more and more powerful computers and more granular models, they're still fed off the same amount of precision in their input data, which means you have a hard limit of how precise that can be. And so we have these weird sets of considerations in space. Like, why is that hard to figure out where something is? Because they don't stay in the same spot. Right? You don't just put something up there in an orbit and it keeps going around in a perfect circle forever. It's being impacted by drag on the top of the atmosphere by different amounts, depending on how, not only their altitude, but also what the sun is doing at that point in time. Because when it heats up the top of the atmosphere, it expands, and the gaseous composition at the top of the atmosphere changes, imparting a different amount of drag on that object. And then you also have all the radiation and heat out in space, and when it's going in the dark side of the Earth, it's going to get cold. When it comes back to the light side, it's going to get heat stress, so you get that thermal stress on these devices. Sometimes that alone can put things into a spin. Not to mention where they are in space impacts how they're going to move. So you get these low Earth orbits. I shouldn't have put it equatorial. Usually they're about 65 degrees inclined, all the way out to geosynchronous orbit. And these ones, like, you might put something in an orbit where they're doing relatively regular periods around the Earth. Then you get things like the Molniya orbit, which is Russian for lightning, where they want to give greater coverage to a certain part of the Earth, so it goes really fast, close down to the Earth and south, and then a really high orbit on the north. So this isn't even, and every single orbit is different. And you're trying to combine all these forces into this really complicated perturbations model to try and propagate, okay, if it was here, where will it be an hour from now? And they drift by sometimes up to like a kilometre a day. If you take where you thought it was yesterday and you say where it's going to be now, you could be off by a kilometre, depending on what space is doing. Near solar peak is probably worse. And also we're launching more and more things into space. I changed this plot at the last minute, but I think this, I also had debris on this, but that just kind of complicated the issue because then you see spikes, which aren't really where they are in time. This is how many things we've launched into space, but then this does not account for the fact that sometimes one of those objects has smashed into 1,000 pieces occasionally, which would give these big spikes where we didn't launch something new, and there has been no mass added, but now there's way more things to keep track of. And so we have not solved this problem. This is an ongoing problem that we as scientists and as citizens and as humans are continually trying to fix to try and make that better, because we do not have enough sensors to keep track of how many satellites were up there 10 years ago, let alone now. And the commercial interest in space grows with access. We're going to get... Also, there are social factors. Like, more countries are developing launch capability because why is it fair that only 5 countries can do this well? And we can't deny them access to space just because we've already junked up the place. And then there's also there's things like the digital divide, where people who don't have access to digital services now can't access things they critically need to live. And so where it might be that you chose to live in a city, otherwise you would kind of accept not great connectivity, that can't be the case anymore. People in the middle of the desert need access to things like online systems for their taxes, for Centrelink, to order food, medicines, telehealth, everything. Everyone in the room who spoke to me about Antarctica will know this. Connectivity is critical to our quality of life. And so what is the role that radio plays in tracking things in space? And it's been there from the start. This is the first paper that was ever written on the idea that we would track things, well, for the public, they wrote lots of things internally, but when they were planning the Vanguard program, the first American satellites in space, they came up with this idea, and there was this lovely quote from one of the reports that was really declassified that was surrounding this, where somebody says, if the satellite were tracked only by optical means, it might never be seen. And there was all this bickering between optical scientists and radio scientists being like, how dare you say that about optical? And he's like, well, it's true. We need to be able to track them by radio, otherwise you never know what the clouds are going to do. So suck it up, we're doing it this way. And they built these networks all over the world. A fun anecdote I love about this is that, you know, all the political context. So we have the Cold War, and we have the Soviets, and we have the Americans, and they're all thinking about putting things in space, but they don't want to aggravate the Cold War because they think if they put something in space, the other country will think it's an aggravation, that they're trying to spy on their citizens, but they really want to do it, they just don't want the other guy to do it. And so they have this moot of scientists. They call it the International Geophysical Year, and they're going to get scientists all around the world to do like they had done the International Antarctic Year a few years earlier, and just come together and concentrate on one particular science and grow humanity's knowledge in that space over 1 year of entirely focused work. And one of the things they were going to do is they were going to launch satellites to have a better model of Earth. And so they went to all these planning things where they sent scientists from these different nations to things like a roundtable in Barcelona where they all agreed no military personnel are going to work on these projects, no military hardware will be used, and we're going to use these transmission bands. And then lo and behold, Sputnik launches, and the US has spent a year building stations all the way down the 73rd parallel, and then that's not the frequencies they used. We'll get back to that in a minute. But there have been multiple networks. They're continually upgraded, not just for loss of capacity, also precision, just the different, the kinds of things we've put in space have changed over time. They used to be really big, school bus-sized satellites, they go into high orbits, we leave them there for ages, now we're going small, fast, disposable. These things change our monitoring profile, our risk profile as well. So we have dedicated instruments. I cannot find a photo of the actual radar. I guess that makes sense. It's secret US Air Force stuff in the middle of the Pacific Ocean. But there's this thing called the Space Fence. That's probably the most powerful one that's in operation today. And there are lots of things that are operated by militaries that are dedicated radars that are active. They're usually like those big curved panels. They point at the sky all day, every day, and they just pull certain types of objects out, log them all day. But we also have people who are trying to turn other receiver-only systems into passive radar receivers, who are listening to things from not just powerful transmitters that might exist from other radars. Like, so there is one of those big dedicated radars in New Zealand, and some of the Australian radio telescope arrays are trying to listen to their transmissions, since they're transmitting anyway, but also ones that are trying to look for reflections from other terrestrial sources like FM radio. And that's going really well, actually, for low Earth orbit. It's pretty good. myself and other scientists are working on other things like commensal processing, which is if you have a telescope that's looking at a deep space source and you're having objects coming through the near field, this currently gets scrubbed by the correlation that gets done in the background. So you have the front end that's completely hardware attached through FPGAs to a back end that does this computation. So by the time data comes out, there's no way to regain that initial information stream. But we actually want to do like slightly different fringe rotation, and we don't want to do correlation without a time offset accounting for the geometric delay. So just like trying to look at the end of your nose and the other side of the room and focus at once. That doesn't work. Your brain can't do that. You need two different modes. So we're adapting these to have those different modes so that hopefully we can not waste information that's already happening while they're collecting data for science. I mean, this is also science, but different kind of science. And so using these sensors, we have, you know, it's radio. You get like frequency and you get phase, you get power, and you use all this to infer so much more information. So like we can tell based on phase difference or time difference of arrival in different sensors, depending on how sensitive your system is. We can get triangulation of position. One of the telescopes I work with has 6 22-meter dishes separated by up to 6 kilometers. That's great for that. We get trajectory and velocity, either looking at Doppler or just tracking observations over time, because we can get down to about 80 microsecond integrations with a bit of software special sauce. We can get a little bit about their functionality, so like if they were transmitting in a pretty regular behavior and then they stop, then we know that something about that has changed. We can get little perturbations, so do you know what microdoppler is? I guess yes. If you track like how the Doppler curve should look if they are moving in the expected orbit, then you would get like frequency over time, you get a sigmoid curve. But then if you get the specific frequency over time and you subtract that sigmoid curve, then you have little smaller scale perturbations. And that can tell you things like whether it's spinning. You get this nice double helix of a waterfall plot. And delay Doppler is how we track things like asteroids. So if something's far away and it's big enough, and we can do that with space stations, if you plot the delay over the Doppler, then you actually just naturally, because it's got a spin relative to you, you naturally get the XY axis and you can get an image of the front face of the thing. It's pretty cool. And also, usually you can tell that something's been impacted, not just because large space stations and stuff have cameras on the outside and they'll be like, there's a hole in my solar cell, but also because you'll see that their orbit will just go, whoop, slightly change. And you can roll it back and be like, oh, they must have been hit by something at this point in time, even though that thing wasn't big enough for us to see. But we did not have enough. So what do we do about it in Tasmania? Did you know we're world famous for radio science? I'm going to guess so, since we had a great conversation before this. So you would know about how Grote Reber had all his poles and fields. And you would know about how he said that Tasmania was the best place in the world based on our ionosphere alone, our lack of temperature, lack of atmospheric humidity. Not temperature. We don't have a complete lack of temperature.
Temperature, but that's another story.
That's not how I aligned that line. But this is actually, I went back further. This is from some early 1800s when they were trying to send different scientists from all over the world down here to observe the transit of Venus over the sun, which only happens every 180 something years. They were basically saying, I know you were going to send someone to Sydney or Melbourne because they're bigger places, but how dare you? Let me list the ways in which Tasmania is superior. And it was just days and days of data and letters and everyone being like, we have these amazing hobbyist astronomers. They've got all the best weather information in the world. They've been doing this daily for 20 years. They've got all these stations, these instruments. They're clockmakers. They help. They're everything. Espousing all the ways that Tasmania is amazing. So even long before the radio people got here, we already thought it was amazing to look at the sky from Tasmania. But we also have a confluence of other factors outside of astronomy and outside of telescopes. Not only do we have astronomy, yes, radio astronomy came to Tasmania, hit it off big time. We got a lot of buy-in from people who would give us instruments or buy us instruments, so we have amazing telescopes. But we also then have that capacity building of people who understand things like clock precision and RF engineering just from working in those fields. But we also have an incredible base of maritime radio and for remote field operations because we are a transition point for Antarctica. We have so many expeditions that leave from here, so we're responsible for a lot of that infrastructure that other places might not be. But also we have this history of being kind of geographically isolated. And one of my favourite things is that at the dawn of the NBN, when we were talking about where we were going to test the NBN in Australia, Professor Jock Given called Tasmania the most connected place on the planet. Wrote a series of essays talking about how the people here have got this certain frame of mind because we were late to get the telegraph, that you could get a call from London to Melbourne before you get a call from Hobart to Melbourne, and that we've all taken that seriously, and in all the decades since, we've gone hard on communications infrastructure, and that this runs deep in the Tasmanian people, which I think is incredible, and it also does come into play here. That means that we have an incredible amount of skills and infrastructure here that we use to support space missions. So typically we don't do stuff in space, we're not secretly launching rockets at UTAS that we don't tell you about, but we do ground support for station keeping. So like NASA and ESA will use us when their stations aren't pointing in the right direction to receive communications from satellites that report where they are themselves, or planetary missions as well. We do Mars Express, things like that. But also can also use that for triangulation, and some of that like figuring out if they're spinning and things, and then we report that back. We do a lot of space weather modelling, so I work mostly with the space weather group. They do this really cool set of experiments, like if you have a planetary orbiter around Mars, and Mars is kind of almost at solar conjunction, then you can watch the scintillation of the return signal to get information about the electron content around the sun. Wow. And we look at how that changes as it passes behind the sun in different conditions and with different tone modulation, and that the physicists do something with that, who knows. And we also use them for radar tracking, though, actually I should point it out, you told me not to leave the frame. The little dish on the lower right has our 7.3 metre dish, and on the left-hand side, this is Mount Pleasant, so we have a 26 metre, and we have a 12 metre, and we have a 14 metre there, and we have other 12 metres around the country that we operate. But this little dish on the right-hand side is actually the star of the show, because it was made for satellite tracking. It was bought off the shelf from China. It came, and they had to get a bunch of grad students to translate all the manuals it came with, but it works a treat, and it can track super fast across the sky, because if you're using an astronomy telescope to look at something that goes 12 minutes horizon to horizon, it does not slew fast enough, and also depending on the mount type, it goes up, it hits a 79-degree elevation limit, and then it has to turn all the way around, and by then the thing's gone, long gone. But we do not have transmit capability, because these things are made to look at pulsars and things, so instead, usually we're doing things using the Canberra Deep Space Network Station, Canberra Deep Space Communication Centre. Very, very cool in general. I think it's awesome. So sometimes we get them to, so we have like some software, but there's also like this special guy who everyone gets him to run his own software. We don't know what's special about him, but if anyone's going to track asteroids in the world, they get this one guy from JPL to run his models and tell you if his numbers match yours. So you call the Magic John and you say, I want to track this asteroid, and he runs his models and you run your models, and if they agree, you're good. And then they set their transmitter to change frequency so that what we receive on our end is a flat tone. And so then we can just use the offset from that flat tone to adjust. Then that becomes our error in our position calculation of where that asteroid is, and we can look at that change over time as an evolution of orbit based on where that thing is. We can do that delay Doppler mapping again. It's really cool. If you don't know much about the station, you can go to the DSN now, and it's just a website that will tell you what it's talking to at the moment. You can think of this as Earth's switchboard. I updated this today. It wasn't talking too much. I probably should have kept the old one. But it's the thing that listens for signals from space and actually communicates, isn't just tracking where they are. So the Voyager space probes, they phone home via these. There are 3 stations that point 1/3 off the Earth, Madrid and Goldstone, Canada, and us. We each cover 1/3 of space, and so there's always one station that's talking to each planetary or space probe, and that's how they get data back to us, basically. And depending on when you look, like this doesn't look very heavily trafficked, but actually at certain points in time it's actually overcapacity, because you have so many things that are out there, especially planetary orbiters, but unfortunately Mars is always in one place, so it means that there are a lot of spacecraft in one zone that are always trying to phone home. But the point of that is to say we do a lot of stuff. We're amazing in Tasmania. We've got a credible amount of telescopes, more than anyone but CSIRO in the country. That's great, but we also can't do much ourselves. We're in collaboration with other places that do space missions, that have more insight into satellite operations, or that know the satellite operators, or that are feeding into those official central data sources that are more closely tied to the military, or that have a transmitter that we don't have. But if you'll forgive me to do just a segue, what has amateur radio done in the space? And what does it still have to do with space today? So when I was saying about how the mini-track stations came online to track Sputnik and then it wasn't there, They did not use the frequency they said they were going to. You might have heard of maybe the greatest citizen science effort in all of history, Operation Moonwatch. You're all going to spit. Operation Moonwatch was where they got amateur optical observers all over the world. At a certain point, it was like 5,000 volunteers around the world to all dedicate hours and hours and hours each day to sitting on these little like kit camera stations and write down when they saw the one of 2 or 3 satellites that existed at the time. And this was used because they then only had a limited amount of pretty limited functionality instruments to properly officially track the satellite. So they had these Baker-Nunn cameras, had a few radars, but you know they couldn't see it in mini-track, and they didn't have enough time to cover everything if something ended up in a very different orbit, and things hadn't been up there long enough for us to really trust what we thought orbits would work like. And so they weaponized the citizens. They were talking about how school children and house mums and the scout leaders and people's grandparents, everyone, they wanted to see space. They would do it. They would do it for science. They would do it for the government. They spent hundreds and hundreds of man-hours each across thousands of people in, 230 teams around the world to say, we saw that one blip of light once, here's when, and then they called someone. There was also...
What year was that?
1957, 58?
Right.
So there was also a radio version. Most people don't know about this part. There was also Operation Moonbeam, but the hard part is it was very, very easy and cheap to manufacture these little cameras, and it's rather simple to make a functional enough optical telescope and to teach someone how to operate that. But the equipment and training involved in weaponizing radio operators was much, much greater, and that didn't have as much success. That's not to say that amateur radio people weren't listening to Sputnik. They absolutely were, and putting a few pieces together. So the first person to locate Sputnik reliably in Australia was the operator of the OTC here in Hobart, Mr. Watson. I'm not sure, is that this building?
It would be this building, I'm not sure.
From right here. Welcome to the hub of the space age where we first detected Sputnik in Australia. Eat your hearts out, CSIRO. So they had this system whereby they were part of an integrated process, that there would be these official radio stations, radar stations, optical cameras that were operated by military people and scientists who would track these things and then feed that information about where broadly they were out to the people via designated newsletters and press journalists that would then go to these amateur groups who would then write down everything and then do their observations, and if anything kind of varied by a certain amount, then they would go into different priority buckets of phoning home, basically. They would get on the phone and they'd be like, we saw it at this time and we were expecting to see it 4 seconds earlier. And that's how they figured out that over a couple of days its orbit had had quickened by 6 minutes or whatever, and that's how they knew how fast it was coming down. And so this was incredibly, incredibly productive, incredibly reliable. This was one of the most amazing citizen science efforts ever made by people who just sat in front of a camera looking for one blip of light and mostly didn't see it. However, in the Soviet Union, they were doing the opposite side, and there's this really interesting paper and set of books also, if you want to read about it. I've loved this, just reading it for fun, that there were actually all of these cultural precursors in the Soviet Union for them trying to ready the population for satellites so that they would be ready with these skills and equipment to track satellites with ham radios, but they didn't want to tell them they were about to launch satellites or what satellites were. So they actually went through all of the community radio magazines, setting up all these obscure scenarios and trends and inserting members and all sorts of covert things to try and get people to buy certain equipment and develop certain skills so that they would be ready when Sputnik came. And it was actually incredibly, incredibly reliable. They did a great job of radio tracking with the people. I haven't managed to get a copy of, there's a particular May 1957 article, which was the first time in the public radio magazine they admitted that there would be a satellite and this is how you can track it. Yeah, and in October it happened. So, probably very rare collectible at this point, but very, very cool story. And so after that kind of went away. And there has been a bunch of amateur radio satellite intersections, like AMSAT, incredibly productive. I'm going to look out for nods to say, do you know what AMSAT is? should I bother telling you again? So there are amateur radio people, and they have launched satellites for you to talk to. And there's the incredibly successful ARIS program, which this is maybe the first thing I ever heard about amateur radio. You can talk to the ISS. And I went, what? Why doesn't everyone do this hobby? That's amazing. But of course, if everyone did it, they probably wouldn't have time to call you back. But amazing, amazing program. And now it's gotten so popular, there's even like there's this big conference for my kind of people, computer people, called DEF CON, which is where all the hackers go. And there's like this popular anecdote that like anyone who knows anything doesn't take more than a notebook to DEF CON because they all just attack each other. It's terrible. But they have this actual whole set of activities, stream of activities that's sponsored by the US Air Force called HackerSat, where they play at hacking actual satellites. So the US Air Force can write down what they did and be like, don't let them do that next time. And so there's things like the AMSAT. So they have all these different programs where you as a person can talk to satellites, and also you as a person have all of the information you need to track satellites. You can go onto spacetrack.org and you can download all of the publicly available information about every object in orbit that has a number and a name and where it's been lately. And you can point your receivers at it. But that does not make a space tracking station, because if you do not feed back into the centralized systems of information that then are used to make decisions, then you're just doing it to tell your friends. So that last jump is missing. Those efforts are not actually doing the job of space tracking stations anymore. There is one incredible program called SatNOGS. You might be able to tell me otherwise, but for the last few years I have been looking. We do not appear to have a station in Tasmania. Why not, I say?
We used to.
You used to, yeah, I used to do it.
Right.
Yeah.
Fantastic
It's
program.
stopped. Brag.
Right, yeah. I thought there was, and then every time I looked at the map, it was like, no, and other people were like, no, there doesn't appear to be. So, don't know why, but SatNOGS, yes, this incredibly successful community science project where they prescribe to you some open hardware recommendations. You can download their specific software. They take a lot of the burden of scheduling and telling you what's going to be overhead and what transmit bands it's in. So network and scheduling support, basically. It arose during one of the NASA Space Apps hackathons in 2014, I believe. Incredible program. And there have also been multiple times where people from official channels have acknowledged that they have used SatNOGS data to make actual decisions. Usually not to be like very precise orbital changes, but definitely to say, well, we gave this particular object a temporary ID because we thought that it was new, but it turned out to be this other object that just moved. Because quite often if we're not viewing things optically, we're just guessing. Most of our identification is based on where something is in space, so if something's really not where we expect it to be, then it usually gets reclassified as an entirely new thing that we just somehow didn't detect before. It's very, very common, but when you've weaponized a whole bunch of actually really, really technically competent amateurs who have invested an incredible amount of time and money all over the world, they make an amazing source of information that is incredibly useful for things, so why don't we use ham anymore? Which is not really to say that we don't use ham anymore, but we don't use ham as first-class contributors anymore. So what could be done when you have enthusiasts that have know-how and gear, and we have this need for information? How can we glue them together? But a better question is probably, why can't just anyone contribute in general? Well, what are the risks at hand? If you assume that any person in the world could log onto a computer and say, I saw this satellite in this particular place, yes, that might pollute the space enough that you wouldn't be able to trust any information. You go back to using the couple of trusted people that you knew about. So we do have to have some form of regulation that at least keeps the information that you're contributing attached to some information about where it came from and how much confidence and precision your instruments have and your processors have. And so we've come up with this thing called the Unified Data Library, which came out of the US Air Force a few years ago. Has been incredibly successful, where it's basically this online data platform where there are data providers and there are data consumers, and then based on your classification level, like military classification, and also service agreements, then you can join those together. So you can say, I want to consume satellite information, I'm going to pay to be on this platform, and then I'm going to pay for a certain amount of data vendors, and then you get access to their parts of the database, basically. And it also provides data in several formats, not just that punch card format, which is nice, you can get proper ephemerides. And that's been going great. But none of them include that confidence metric, none of them include things about precision. They still don't really give you any information beyond the vendor that provided that information. It doesn't say what station it came from or anything. And you can't enroll just as a completely random person. And there have started to be mutterings from the Air Force about incorporating completely random people in their sensors. If anyone can figure out how you get internal Air Force reports, good luck, because I found this cited in a bunch of US Air Force University theses reporting and quoting this particular internal broadcast that I do not have access to. And I know other academics also want to read about. This is apparently their strategy for, okay, well, someday people are going to want arbitrary access to contribute data, so what are we going to do about that, and how are we going to do quality control? The little different bits that I've seen that cite this report basically say a set of rules of, like, they need to say what confidence, what precision, what equipment, what everything, they need to be available a certain amount of time, blah, blah, blah. And then a whole section about how they must exceed the performance of dedicated SSN sensors, otherwise why is it even worth it? So if you can't build something that's better than the space fence, don't bother. Which doesn't really seem fair, because I think that we have the potential to provide an incredible amount of support. Maybe you wouldn't go immediately to, we're going to let this person just tell me where an object is completely blind, sight unseen, but you could say yes or no to existing detections. This seems right, this doesn't seem right, and maybe if it got seen 4 times in an orbit by official sensors, it might be seen 25 times by other people in that time. You might get a much better idea of how to interpret those official data points that they had, but you could also more effectively detect maneuvers, because quite often one sensor sees it. By the time it gets to another great sensor, sometimes it has to pass all of Asia before it hits another one. It might have moved, but at what point did it move? Because that matters. You might not be able to see the difference in where it's detected now, but you will see it 4 orbits from now. So getting that information faster without having to get multiple data points and then back propagate that model is going to make you much more effective at detecting perturbations if that maneuver didn't go as expected. Also do handover coverage, which is, yes, if something's not going to be seen for a while, you might be able to just report that, yeah, things are where they're expected, or pass information from station to station as they're passing overhead. But also transmission behavior profiling, because even though we have all of these radio sensors listening to the skies, so many of them don't have official information about what the transmission behavior is supposed to be. We're just listening for a signal, which we can use to triangulate the thing, and we're looking for something kind of in the right band, because we want to know it's the right object, and we're using the right receiver in our telescopes, because we have multiple. But knowing whether it's polluting the spectrum is actually really important, and some great research actually came out of Western Australia recently, where some of the people who operated the Murchison Radio Observatory started pointing their very low frequency, in my mind, their VHF antennas at Starlink satellites, and found that even though they weren't supposed to be transmitting in this band, they were emitting a huge amount of mechanical noise. And so there are all of these things that we're not accounting for that aren't allocated in the spectrum, and that just makes everything a nightmare for everyone. But there are all these little bits where more information might contribute so much more and might make so much richer the information that we already have just by people working together. So why don't we do that? And yes, we do a little bit of that. So why don't we do more of that here? That's the end of my presentation that I brought for you formally, but I thought we would also have time a little bit at the end for a chat, if you would like. So thank you for listening to my spiel.
Now, questions for Mars or different rabbit hole?
I was very interested to hear you talk about the what appeared to be using FM broadcast stations as
Yes.
transmitters for effectively passive radars.
Yes.
Is that something we have here in Tasmania operating, or
No.
no?
So there was this famous thing where another one of the Murchison VHF antennas was listening to FM radios that they managed to reflect off the International Space Station. I believe this was in 2007 or something really early. I'm probably misquoting that date. Thereabouts. 15 years ago-ish. They managed to detect the ISS reflection from FM radio on this particular radio telescope, and then there was a few kind of funding round, kind of interest things, and so one of the companies I worked with, actually those folded dipoles, that comes from a company called Silentium Defense, and they came out of a CSIRO-based incubator program for people looking to leverage kind of like unexplored avenues in space instrumentation maybe 10 years ago. And so they went through the CSIRO incubator going, we're going to follow what the MRO have done, we're going to figure out a way, or at least investigate whether it's feasible to kind of productionalize this. And they've made a whole company out of these little folded dipole antennas. They're on a metal mesh. They put about 64 of them in a right angle and they're separated enough that they manage to get triangulation. They can detect medium to large objects up to high Leo, pretty effectively. I've been with them during one of, so there's this.
When you say medium to large, are we talking the size of a bussy, or are we talking the size of a carton of beer?
Bigger than a carton of beer, but maybe meter cube. Yeah.
Okay.
Not at really high. Yeah. So obviously bigger sizes closer. So
Sure.
you might not get a meter cubed at 1,000 meters up, kilometers up, but you will at 300, 400.
It needs to be about a wavelength at least, doesn't it?
Yeah. Depends, but they actually have this thing called. Oh, why can't I think what it's called? They have basically this coordinated campaign. So if you've ever heard of how everyone's really panicked about an asteroid hitting the Earth, so NASA started doing this activity where they would get everyone to pretend an asteroid was hitting the Earth, and then get all of their teams and systems to pretend that was happening to figure out how effective they are, basically. We do that. We have satellite war games. Where,
Simulation?
no, real. So all different people who think that they have satellite tracking capabilities will log on with the US Air Force and people all over the world for 3 days or sometimes 5 days, and then just track satellites as best we can. But because so often this field is really wide open, that any information you can gather is good, and we all feel good about tracking the same. We've all seen the ISS a million times today. Whereas this is we want you to track this particular thing, and we want you to track it now because we're going to pretend it's about to hit something. You need to tell us in, 2 minutes from now what maneuver adjustments it should make. And so we play this game where we all turn our sensors on and try to respond to real-time threats, basically. And I was with them for one of their campaigns, and I was really, really surprised actually how effective it is. It was reliably, well, actually, some things it doesn't detect and we don't know why. Landsat is pretty big, and it will get half of them but not the other half, even though they're all the same form factor, which is really weird, and they're all in about the same orbit. So it's not super reliable in that you also have to account for the kind of issues with FM. You don't know if there's now dead air, or you don't know if they're changing things about their habits. So we use a line of sight antenna to the FM radio transmitters. So this is in northern Adelaide, northern Adelaide. So all the FM transmitters along the Adelaide Hills in Western Victoria, they have kind of calibration, just Yagi antennas, that they point to then get a signal, and then they look for reflections of that same thing and then do the comparison, basically. And so then if they see something that's about the right size and about the right direction, moving in about the right way, they're like, oh yeah, then that's what we're looking for. And then their computer systems can do scheduling to look for things in certain echoes. And yeah, that's just delayed Doppler mapping too. So it all happens in software. So it's actually quite interesting, because that was the first time I got to work with something down in those lower frequencies. In high frequency, so many things happen in the front end. Everything's cryo-cooled, and you're trying to push everything through low noise amplifiers. You want to have a highly directional antenna. You're doing all the stuff that by the time it gets to the digitizer, it's just pretty much good now. That's as good as it's going to get, and the computation you do is just about doing comparisons and accounting for geometric delays and things. But in the lower frequency antenna, it was just what comes off the antenna is just straight up mess. And everything happens in software. They're pulling magic from that data stream. It was amazing. But the science is all there. We know where it's supposed to be, and radio is magic. You can get a lot of information.
So
yes?
If you're running an FM station and you're tracking a satellite, what sort of range have you got to the satellite? So what's the actual visibility time for you to receive it?
So at the kind of altitudes we were looking at, you were sometimes getting 2,000 kilometers.
Okay.
Yeah, that's pretty typical.
Yeah.
But these are regional radio towers, I guess, might make a difference. So they're very, very high power. So what we're talking about when we're tracking asteroids and we're using the 20 kilowatt transmitter on Tubumbilla, all the astronomers are that's incredible. And they're using hundreds and hundreds of kilowatts. This is our 800 kilowatt transmitter, because they're made to get people their news and media.
It's actually being DAB. I was going to have DVB, might be digital TV. Line system is 1.2 megawatts.
Right.
From Mount Barrow. So and that's a nice big thick band of
Yeah.
transmission. So I don't know if that would be a different way of doing it compared to FM, or whether it would add any value.
Yeah. We don't have any of the right kind of antenna in Tasmania, and I guess in Adelaide, they just went off that because they did some like
Had the-
proof of concept stuff out in the field, and they were like, we can pick up these stations, and they've just used those stations. But that might evolve over time. And I guess if it didn't work very well, they would immediately find other means, but it's working pretty good, so they haven't had to. But they are, at the moment, trying to develop like a deployable version. So those dipole antennas, they're about 800 mil. And so the whole assembly might be, 40 meters square kind of. But they're trying to make a version which you can sell to someone in a shipping container. And so they're the smaller ones, and the mesh is rollable, and so I guess, probably less protection from ground noise again. But they're pretty simple. They account for each other's nulls, and they're surprisingly effective antennas. So I imagine if they get to those slightly smaller antennas with slightly less controlled environment, and someone hasn't gone out with a ground compactor and made it perfectly flattened laser ranged where every antenna is relative to each other, then they might have to do more accounting for transmitter performance. But yeah, as it stands, I haven't really had to.
Mars, we've got a question. Is there any reason why a couple of strategically placed satellites couldn't assist in tracking other satellites apart from cost?
They do. So there are satellites. This is another thing about like sophistication. It used to be that when you launched a satellite, it kind of had all the bells and whistles. You were going to put something in space, so you may as well give it everything, including the kitchen sink. Like by the time you put it in a rocket, you may as well bring everything. And so they're big and they'd be complicated, and they'd have all sorts of transponders where they could talk to other things, and there were lots of satellites in that earlier era which would basically listen to GPS satellites to tell them where they were, and then phone home to say where they thought they were, and then get updated whether they were where they thought they were, and then they had some internal model of where they thought they were. But nowadays the sats are dumb, and we don't want to give them more receivers than they need, and they're like this big, and they move around all the time. So yeah, it's not super effective for certain types of objects which are becoming more common. Like they're trying to launch things. A few years ago, someone tried to launch these things called space bees, which are about the size of a sandwich, into space. And the FCC in America, for some reason, is the one who could actually say no to this, because all the launch providers and everything were like, well, they do have money though. And the FCC was like, actually, no, we've decided that this is infeasible because it'll be too small. We won't be able to track it from the ground. It makes too high a debris risk for everybody else operating in orbit. So they just paid an Indian launch company to launch them anyway. You got a $900,000 fine. They went, thanks. Also, can we launch the next ones now? And the FCC went, oh, well, you're going to do it anyway, aren't you? Go on. So we have very little control over what's up there. They're getting smaller. They're getting crapper. They don't have smarts. They don't have any idea where they are. They move all the time. And also, when you have that many up there, then they're all unreliable reports for each other. So GPS are pretty trustworthy, and if something can keep an internal model and have reliable enough instruments that it can talk to GPS, we do trust them to say where they are, but that's still generally not enough.
So from a GPS point of view, the devices which are above the GPS satellite orbit still are able to use GPS data, I assume. It's just reporting that they're actually above, because they're all down facing, I assume.
They're as directional
so if
as they
something
can
is
be.
above it, it's still able to use the GPS satellites to pick up those time signals, even if they're above them.
Latitude and
Like
longitude.
Typically-
higher orbits.
Typically, higher orbits are going to be more complex, more sophisticated instruments. So they're going to be things like really large comms, or space telescopes, or like really sophisticated Earth observation stuff. So yeah, they're normally the smart ones, which are enough that they communicate with the ground enough that they can kind of operate themselves. It's really, as you get closer in, the more craft, the more crap. And so those higher orbits are sometimes those ones that have been up there for decades, just quietly plodding away, doing their job and not causing any trouble. Higher orbits are not our concern for the most part.
And not yet the 40K orbits and all that sort of stuff.
Yeah, they're not used as much anymore, just because those 65-degree elevation, 400 kilometers up orbits have just become totally standard. Everyone's trying to get in that same orbit. Yes?
Just clarify for me, please. I think you said earlier that some of the satellites are transmitting out of band.
Yes.
and causing interference.
Yes.
First question is why? Because if we do that, we get a ton of bricks down on top of us.
Yes.
And secondly, how does that affect other satellites and the reliability of the information coming from other satellites?
So same answer to that. They all speak crap, so you can't trust a word any of them say about each other. But the reason why they don't get slapped so often is just because our ability to police things that are happening in space is just really poor. Like if you tell off a vendor, hey, your satellite's doing something it's not supposed to, they'll be like, well, it wasn't doing that on the ground, so it must be broken, and what are we supposed to do, go up there and fix it? And then they get let off scot-free. But they do, it's not super frequent that they'll transmit out of band. There is like mechanical noise or like shielding leakage issues, which they couldn't have accounted for in well, if they did a good job of their manufacturing, maybe they would have done good vibrations tests and things like that, but those standards are just dropping. So there are going to be things that arise while in space that you just can't help, and there's nothing, like you can get them in trouble for it, but if they can't do anything about it. And also not everyone checks very often, so if it's doing up to the astronomers to just come up with it this year going...
Whose jurisdiction is it? Like...
Depends on the country.
Do the people, like when you're talking about a vendor, is that like, if they're a German company, is it like somebody in Germany has to tell them off? Like somebody in America can't really tell off in Germany?
I mean, it's like if space junk falls on Australia, like we can find them for littering, but but there's not an international agreement. It doesn't really work that way. So the same thing with like an American vendor doesn't like what their government says about it, so they're just going to go to a different one. Like it's just completely unmanaged. Like nobody wants to agree, because if we start making rules for each other, we have to abide by them, and nobody wants to be the first one to make rules in space, because everyone wants to secretly be the only ones who are allowed to do things like mine the moon. Everything is about how we don't want to make rules about what you can put in space, because what if we want to mine something and we need instruments like this thing we just banned? They'll never be able to walk it back, and so they under-regulate as a precaution. Yes.
With your comment about frequency changes due to mechanical noise, are you talking about vibration, and that vibration getting into modulation of the satellite or varying its frequency?
There's been a few things where also like sometimes like unshielded power sources, depending on the size of the thing, it's a bit out of my purview. I know that hardware can emit stuff depending on what horrible conditions you put them in. And I do know that this has been seen out of band, usually by quite sensitive instruments, but that's not to say that they're not important. If only our astronomy telescopes are being affected by these things, and there's still very expensive infrastructure to be affected by something that shouldn't be happening. So yeah, I'm not too sure of the cause. I do know what people have written about it, but that's not my science. Sorry. Yes?
Iridium put out a paper because when they were doing their last satellite changeover, and it was fascinating. It was basically talking about this is how they deorbit.
Yep.
And the steps that they go through to deorbit a satellite were just so far beyond what I thought about, like severing connections internally. But this was all designed into the satellite when they built it.
Yes.
So it amazes me what you're saying, that there's no some sort of agreement or treaty amongst those who launch satellites to say this is how we're going to do it well.
Well, there's a few things. So it's usually based on, commercial agreements, things like that. Like the greatest authority is, I won't give you money if you do it this way. That affects people way more than laws at this point. So the ESA has a lot of agreements where they won't partner with someone or they won't launch something if they don't fulfill certain quality criteria. And so they had a few, in 2005 or something, another Ariane rocket exploded in orbit again. It was like the third one in 10 years or something. One time it took out one of their own satellites. It was very sad. But they came up with this passivation laws where if you put a rocket body in orbit, they need to vent their remaining fuel so that they have lessened explosion risk. They were still exploding all the time. Then in 2005, the ESA came up with a set of rules saying that everything had to be deorbited, planned to be deorbited within 25 years. So if you put something in orbit, you had to have a specific set of steps of things you were going to do to ensure that this thing would come down 25 years after its end of life. 25 years after it stopped functioning. That didn't seem that severe, but everyone got up in arms. And still, then they did a follow-up saying that, 10 years later, actually only a third of people have done it. Even all those people that we made fill out all of these regulations and tell us about how this was built into their hardware plans and everything. And it was like, 1/3 of them tried to go to, so this wasn't bring them down, this was bring them up, because they're geostationary, so you're supposed to put them in graveyard orbit, hoping that's not an orbit we'll ever need. But they try to put things up, and they found that a third of people didn't do it, another third of people tried to, didn't get far enough, and just came straight back down, and then only a third of people did it effectively. And then when you get to low Earth orbits, then you get problems of like, then they can claim, well, what are we supposed to do? Bring it down if it's not functioning properly? Well, if we can't control the descent, we're putting people at risk, so actually maybe we're safer leaving it up there because it's less immediate risk to humans. They kind of have a point, depending on what it is. I mean, if it's this big, it's not going to make it to the ground, but other things, that might be valid. And to the point of quality controls, there's also like a fairness factor. If the couple of countries that have had decades to perfect their technology that's going up into space now goes, okay, well now we've found state of the art, and we're not going to let anything less sophisticated than this go into space, then all of a sudden every other nation who hasn't reached that level of sophistication is just going to be locked out of that sector forever. And they're just not going to listen to your rules anymore. But we shouldn't make them in the first place, it's not fair. So we just kind of have this challenge of, we can say that our things should fulfill these certain quality controls, but it's not really fair for us to tell everyone else that they have to when they haven't had time to fail and practice. And then if there are other countries out there who are allowed to launch things that don't fit these quality controls, then people in our countries are just going to go to their companies to launch the things. So it's kind of stuck.
And it's a tough one, because if you're providing a service, and I'd imagine the investment to do all of that up front and do it well is significant.
Yes.
And then you're competing with people that
They're going to do it cheap
there's a
and
massive
fast.
saving on their part. But
And even if
as
you
a-
design
as an
something
end user,
amazing, it
like
could just break
I don't know
anyway.
what, you know, Optus's deorbiting plan is as opposed to Telstra's for their satellites.
Oh,
But
no.
I make that decision. I mean, I would assume that both.
I actually don't know. I mean, we have the NBN has the Skymaster. Skymaster. Yep, Skymaster 1 and 2. And they have very, very, very well engineered. They have proper procedures, and they were made to high machining quality and did great tests and everything. But anything that's not like an official envoy of a particular country, I imagine, gets drastically lower in quality very, very quickly. But even if you did build something that was completely sophisticated, you ran through all the tests, space is just kind of hectic sometimes. You might do all of that and test it for years and then launch it to space, and then one thing breaks, and then you've wasted all this sophistication in this model that you put up there.
Or it
Which
gets
is why-
triggered earlier and brings it, takes it offline, you know, a year after it's been launched instead of 25 years after it's finished with it. Like that.
Yeah. And so you also have this thing where like, okay, well then maybe we'll just make unsophisticated ones just as a practice, and then we'll work up to the good one, and then they never get up to the good one because the simple ones work and it doesn't really cause any immediate commercial impact to you, so why wouldn't you just do that? But also, yeah, there's just infinite defensibility. If something hasn't come down, you can just say, well, it was designed to, it just didn't work, and everyone goes, well, space is hard, fair enough, off you go. Yes?
Are there any programs that are actually looking at how we can remove some of this space junk, or
Yes.
actually go and clean it up? Or?
There are lots of things that are proposed to bring down space junk. The problem is that there are about 30,000 things that are tagged and numbered and everything. They're bigger than, 10 centimeters cubed. That's what we can reliably track from the ground with all of our different networks. Smaller than that could be 100 million, 200 million, some people say, depending on the models. Usually the way that we estimate how many fragments up there are smaller than that, when we have a spacecraft that goes up and then come back down, we look at the impact surface and see how pockmarked it is, and then run models, scrape little bits of material out of it and tell whether it was a rock or a piece of metal that hit it, and do all sorts of complicated science. It's not my deal. But that's how they kind of figure out probabilistically about the distribution of non-visible debris, which is lots, orders of magnitude more than we can see. But then all the programs to go up there and get it are like, okay, well, we can attach a sail to it, which will, increase its drag profile, and it'll come back down. And we'll get a little claw machine that will get it and take it back down. Or we'll, get a mothership that will, like, magnet and hoover them all up and everything. But it's still just grabbing one piece at a time. And in the time that you've sent that mission up there, somebody will have launched, like, 65 new satellites. And before all that, if we don't have a high precision on where that object is, all of a sudden your machines then need to be really, really autonomous, and we don't really have that level of sophistication yet. So if our ground tracking isn't very good, then our ability to grab things are kind of limited by how well we know where they are. There are things where if you shoot lasers at the atmosphere and you kind of excite a certain region, then you can bring down very small objects. called a space broom, but it's just very complicated to use, and it can't get anything that's very big, and so it's kind of removing the junk that we already didn't know were there.
Very James Bond. So, any final questions for Mars?
Yeah, I was just going to ask, I think there's a thought that we'll get to a tipping point where so many things are running into each other, scattering so many more things that run into each other, and the whole thing multiplies up. Is there any thought about how far away we are from that tipping point?
So this hypothetical scenario is called the ablation cascade.
Right.
Oh.
And we have no idea.
No.
Based on different models, it should have happened maybe 10 years ago, or it might happen 15 years into the future, or we don't know, because it's based on dynamics that we can only guess at. But also there's such a random element to whether things hit each other at a certain time, and it kind of is based on one really bad collision happening in the wrong spot between the wrong objects for that to set off a chain of events. And so every time that doesn't happen, that was just chance. Technically, for every moment that we've had objects in space, they might have only, like, two, if we only have 2 satellites in space, there's still a chance they could hit each other.
Sure.
It's just less. So we're increasing those chances, but it's still random. So maths has worked in our favour. Thank you, mathematics. But it's, yeah, obviously at a certain point you're going to hit dynamics where they can't not hit each other. We are trying to catch up with those policy decisions, with those engineering decisions. Whether it will happen in time, none of us have any idea. There's no even guideline.
What scale of size is involved where things don't disintegrate on re-entry but actually come down to hit us?
Well, there's things like rocket bodies, they come down. So like, I think it's estimated it's about 1/15 of something could feasibly make it to the ground intact. So yeah, if something is 15 times bigger, then would cause a risk to you. But also so much of the planet is water. Things come down all the time. They're just, the odds are in their favour that they'll hit the ocean. So we just don't see them very often.
And is it fair to say that most of those launches are towards the equatorial part of?
Yes,
Yes.
but they will launch that way,
Tasmania is not
and
high for a rocket body?
then they manoeuvre. So no, actually the opposite, because 2 things. One is those first stages will go equatorial, and then if they want to do an orbit change, then usually the second stage is going to be involved with that, unless you go into things like Starlink, where they actually fully deploy them in a lower orbit, and then they have manoeuvring capabilities to do an orbit raising. That's very recent. Usually you would use a second stage or third stage rocket to do that orbit maneuver, which means that rocket gets left in a higher inclined orbit. And because there's water everywhere, and we think it's safe to crash into the ocean, we have this Point Nemo, which is the furthest point on the globe from land. It's bottom of the South Pacific Ocean. We try to crash things there. So that's where the Mir space station came down. That's where tons of satellites have been crashed. They're down there under the ocean. You're not allowed to sail there or scuba dive. No. Go figure. But when we're trying to crash something, if you think about an orbit that... do not draw. That's going to be too small. So if you think about how you have an orbit and you kind of have these 3 axes of uncertainty. You have the along track, which is how forward or back along that orbit it is. You have the cross track, which is how kind of left or right, like latitude it is. And you have the radial, which is its altitude. This one doesn't get as much error in our detections, just because it would have to be pretty hard perturbations for it to be wobbly on this axis. But radial is going to impact its speed really heavily, and a long track is going to impact how far it goes really heavily, and those 2 things also work together. And so our estimation of what kind of path it's on and the orbit around the Earth is really quite precise, but when it's coming down, how far along that track it will go before it comes down is really imprecise. So when we're aiming at the bottom of the South Pacific, if you just crash a little bit earlier, guess what's underneath you? The Bass Strait.
Thanks, Murray. Before you asked the question, I figured we were saying.
Which is why I have a pen pal on Cape Barren Island who is writing me fantastic... What was that thing that came down the other night? My dad got it in his phone. It's like, again, another one. Yes, you're going to see them all the time.
Just don't sail on the boat when it happens.
Mars,
Yes.
I was thinking from one of the other speakers, if there's 30,000 bits of satellites and junk floating around up there, and
Yes.
that number keeps escalating,
eventually in the future, will not investors start to have second thoughts about investing in some of these satellites if there are more collisions and there's a potential of a lot more collisions up there? Is that something that they'll start to consider if we don't eventually start bringing more down and getting more space between them? So
I think
there's
this is
less
more
risk
of an
of
economics
collision?
question than a technical question. My instinct would be to say no, because while there's a resource there to exploit that you know people will pay for, even if that thing is just orbital space and being able to provide a service, why would you stop until you are made to stop? People have demonstrated time and time again that they will not.
Elon's
They'll-
proven that.
They'll be like, this will be my last chance to launch something before we can't anymore. Let's be the last satellite service on Earth.
Okay, the next step from that onwards is how do you mitigate the risk of these collisions which are inevitably going to occur? Do people have, like, to the military or whatever, have satellites ready to launch as spares to put up in case their main strategic satellites get taken out?
Not that I know of. Don't think so. But, you know, they're figuring that the odds of a particular satellite being destroyed is quite low. And we do have the ability to see, this is... Defense really drives motivation sometimes. Because we're in kind of this, like, angsty moment with China in particular, different countries have developed satellites that are able to pluck other people's satellites out of orbit. And there have been a few tests in the last few years where a country has taken one of their own satellites, launched a satellite to slowly creep up to it, grab it, pull it into a completely different orbit hundreds of kilometers away, and then back, just to show they can. Just to show that if somebody else messed with them or started surveilling them with a different country's satellites, then they could just get rid of it. And so very large satellites, we can move out of the way, even if they themselves aren't capable of moving. So large satellites are more likely to have their own maneuvering capability because they're going to be larger, have more internal fuel, usually are more sophisticated, so they have things like thrusters. But even if yours was broken, you could probably get someone to grab it. So it's really the smaller satellites where it's kind of like we have so many of them, who's going to miss the loss of one Starlink or something like that. It only creates a problem when then it hits something else.
So you have a few spares up there hanging around.
Yeah.
Somewhere that needs you put them into the position like they do now.
Yeah, so these mega constellations just kind of have built-in redundancy, and everyone figures that the odds are in their favour that something like that is going to be hit first, and then we'll have enough warning to do something about it. But again, it's like a Carrington event. It's just like the preparations we could make would have to be so extreme for an event that is so unpredictable, we just don't bother. It just doesn't fit in the human brain.
What would be easier, to grab hold of a satellite and either change its orbit, send it down to the atmosphere to burn up, or send it off into space ad infinitum?
Depends how high it is. If it's in like middle Earth orbit or lower, it's easier to go down. If it's higher, it's easier to go up, not necessarily by forces, but just safer to go up. You're not going to hit something with a completely uncontrolled descent down multiple orbit regimes.
On that, you mentioned before about higher up satellites, pushing them into a higher orbit and let them just hang around there. What stops them, instead of going to a higher orbit, basically just ejecting them? Is it just too much to totally escape orbit altogether? Or
Yes.
we don't want to? Okay.
Though they have started that. There was a few experiments. They've started crashing things into the moon, but then like if we end up on the moon, like that might matter at some point. So I don't know if I agree with that. Mixed opinions. I guess if it's between that or coming down in an uncontrolled way, maybe that is the lesser of two evils. But all of these are just debates about what's a lesser evil. It really depends on the particular object, what capabilities it has, what orbit it's in, when it's coming down, and who cares. It's very case by case.
Can we show our appreciation? Thank you, Mars.
Do we turn this off?
That's all right,
Do
we'll
I
do that.
just say goodbye to everybody?
Yes.
Thank you in the north.
We had lots of debate about how to actually get rid